Hello, we're now at the very exciting topic of electromagnetic induction. But before we dive into all the exciting stuff, I have to make sure that you know the difference between these three quantities. Magnetic flux density, symbol B, magnetic flux, denoted by symbol phi, and magnetic flux linkage, denoted by the uppercase phi. So let's say we have this region here, a uniform magnetic field B, and let's say we have a coil which has a cross-sectional area of A. Then we say that the flux of this coil is B times A. Let's use some numbers. Let's say the magnetic flux density is 2 Tesla and the cross-sectional area of this coil is 3 meters squared. Then what is the flux of this coil? 3 times 2, 6 Weber. So Weber is the SI unit for magnetic flux. So the magnetic flux density is kind of like the rain intensity, and the magnetic flux is kind of like the amount of rain passing through the basin. So the flux density could be the same everywhere, but if you have a bigger basin, you have a bigger flux. The orientation of the basin is also important. So if you want to capture the maximum amount of flux, naturally you put the basin perpendicular to the rain, right? Because if you put the basin parallel to the rain, you get zero flux. So coming back to this diagram here, this was when the coil is facing the magnetic field directly. That's why the magnetic flux is B times A. If the coil is lying parallel to the magnetic field, then we say that this coil has zero magnetic flux. You know what's coming next, right? So what if the coil is placed neither parallel nor perpendicular to the magnetic field? So something like this. How would we describe the orientation of this coil? You can say that the plane of the coil makes an angle beta with the magnetic field. Or you can say that the axis of the coil makes an angle alpha with the magnetic field. So back to the question, what is the magnetic flux of this coil? Two ways to go about it. Either you resolve the coil or you resolve the magnetic field. This is probably the easier way. You can see that the effective area of this coil is actually this area, isn't it? You can see that the amount of magnetic flux passing through this coil is the same as the amount of magnetic flux passing through this coil. And the area of this coil is A sine beta, because this angle is beta, right? So this angle is beta. So instead of this area, you want this area. So this is the opposite side of this right angled triangle. So A sine beta, which means the magnetic flux of this coil is actually BA sine beta. The other way, as I said, is to resolve the magnetic field. So you want to resolve this magnetic field into two components. One that's perpendicular to the coil and the other one that's parallel to the coil. And you know that you can ignore the components parallel to the coil, because when the coil is parallel to the magnetic field, we said that there's no magnetic flux, right? So we are only concerned with this component, the component which is perpendicular to the coil. And hopefully you can see that this magnetic field is B cosine alpha. Look at this magnetic field line, yeah? This one, and this angle is alpha, right? So look at this right angled triangle. So this component is the adjacent side. That's why it's cosine alpha. So the magnetic flux of this coil is BA cosine alpha. Now some of you may find it very difficult to do the resolving, right? If that's the case, I always suggest you do the guess and check method. So you just anyhow guess. So maybe you guess it's BA sine beta, because there are only two choices, right? It's either sine beta or cosine beta. So if you guess that it's sine beta, then you ask yourself, what should the magnetic flux be when beta is 0? So when this angle beta is 0, it means that the coil will be parallel to the magnetic field, which means magnetic flux should be 0. So sine 0 is 0, right? So you guessed correctly. Because if you guessed cosine beta, then cosine 0 is not 0. Then you know that you guessed wrongly, right? Similarly here, this one. If you were using the angle alpha, you could have guessed either cosine alpha or sine alpha. So you just ask yourself, when alpha is 0, what should the magnetic flux be? So you look at the diagram, when alpha is 0, it means the coil will be perpendicular to the magnetic field. So you should be getting maximum flux of B times A. And cosine 0 is 1. So that means you guessed correctly. Get it? So hopefully now you know the difference between magnetic flux and magnetic flux density. But there was one more, right? The magnetic flux linkage. This one is very easy. So sometimes your coil doesn't have one turn only. You could be having a coil with many turns. So if the number of turns is n, then the magnetic flux linkage of this multi-turn coil is simply N times B times A. It's kind of like the total flux passing through all these many turns of coils. Easy? Alright, that's all. Ta-ta!